Hello all, this is the video solution to group work D5 for the potential energy stored in a spring. The first question tells you that you have an object that is attached to a spring. It's sitting on a surface. The friction is frictionless. The mass of the object is 0.15 kilograms, and it gives the spring constant ahead of time. That means that it will take 9.5 newtons to stretch it 1 centimeter. So this is the setup that we're working with for the remaining problems. So the second set of questions says that you're going to pull this, he's pulling it, which means he's stretching the spring. You pull the mass in the positive direction until it reaches a position of 15 centimeters. And along the way, he can measure the force at each of these other positions. So this is the equation that is used to relate the force of a pull on a spring and the displacement of the spring. It needs this value, K. This K is called the spring constant. It means how much force is necessary per length change. So this is the equation that is used for the following 4 questions. And you just substitute the various values in as necessary. So I only demonstrated the work 1 time. But at 3 centimeters, it would take 28.5 newtons to pull it 3 centimeters. It would take 57 newtons to pull it to the 6 centimeter mark. And then conversely, like the spring is also pulling with 57 newtons when it's at the 6 centimeter mark. So at the 6 centimeter mark, you could imagine that here's the force of the pull by this kid named Robert. And then here's the force of the pull by the spring. So the force of the pull by Robert is to the right. The force of the pull by the spring is backwards. And then, of course, you still have your gravity and your normal force. So these don't change at all because the pull by the person and the pull by the spring are horizontal, and it's on a flat surface. So in this case, gravity and normal force are equal. But as the spring gets stretched farther and farther, this value increases, and so does this one, because it's not accelerating. The leftward pull by the spring is equal to the rightward pull by this kid named Robert. So you can solve the last 2 questions using the same values. Force is equal to the K value times the displacement. So if you did this for 4 or 5 different values, you would end up, you can't really see, but I did plot the points on here. So here's my point at 6 centimeters. I went over the 3 centimeter. You can't even see it. It's so perfect. And then at this 12 centimeter mark, so I drew this line right here, and this line represents the relationship between force on the spring and displacement of the spring. Now, we've already covered this in a lab, but the slope of this line is called the K value. That's how, it's the number of newtons, so it takes, if you added 100 newtons, you would stretch it almost 11. Yeah, that's true. A little over 10 centimeters. So the next question asks you to determine the average amount of force. So he starts with 0 newtons of force and ends with 142.5 newtons. And so the average of those 2 numbers is right in the middle. So that's this middle value. So like thinking about it in a different way, if you took this value, if you took this graph, like the area under the curve of this triangle would be the same amount of space as the area under the curve of this green rectangle. So this is actually really important. The area under the curve represents the work either done on the spring or stored in the spring. Work on spring is area under the curve. I have more of that in the next slide, but this is it. This is the idea. Okay, for a force versus displacement graph, the area under the curve is the work done on the spring or energy stored in the spring. So question 4 asks you to determine the work that Robert has done. So we took 1/2 of the maximum force times the displacement because I used the average amount of force. So force times displacement will give you this many joules. So this is what I was talking about before. The spring is pulling left, but the displacement is to the right. So the spring has negative 10.7 joules, or it has done negative 10.7 joules of work on the box. And Robert did 10.7 joules of work on the box. The next question asks you to determine the amount of work it took Robert to go from the 6 centimeter mark to the 12 centimeter mark. So if you went all the way to 12, it'd be 10.7. But just 6 to 12 is only that area under the curve. So that's two separate shapes. You have this triangle space between 6 and 12, and the force goes from 57 to 114. And the length or base of the triangle goes from 6 to 12 centimeters. So to calculate this area right here, this part of the area under the curve, you need 1/2 of the height times the base. Now, I'm putting this in meters because joules are measured in kilograms times meters squared per second squared. So that's actually kind of important to make sure that you use meters, even though the measurements were done in centimeters. Because if you're going to report something in joules, the units must be kilograms times meters squared per second squared. So the top half of this shape is this triangle right here. So 1/2 of the force times delta x. And the bottom half, it's not half, but like the bottom part, is just the force that you start with times the length that it is stretched. So the force that we start with is 57 newtons, and it's stretched for 6 centimeters, or 0.06 meters, to produce an overall work in this section of 3.4 joules. So by combining these two numbers together, you can determine the total area under the curve is 5.1 joules. So this is the written description using words for the definition of work and how it's related to the graph. So the area under the curve of a force versus displacement graph, that's the work done on the spring. Also, it's the amount of potential energy that is stored in the spring, if you're looking at it from a different perspective, if you make the spring the system. Question 8 asks for a general equation to describe the potential energy of the spring as a function of position. So this is like a brief summary of what's being asked. So if you start here and end farther, we want this middle section, so we don't care about this value right here. We want just the change in position. So that if the initial force isn't 0, and it's like some other initial force value, we should still be able to determine what the change in energy is based on this value. So here's the idea. The potential energy stored in a spring at the initial length is 1/2 of the distance times the force. All right, so this is Fi. So 1/2 Fi times the base. So that's 1/2 base times height. And then separately, remember that force is the K value times the displacement. So all of the energy stored at this portion right here, the initial spring potential energy, is 1/2 kx squared, by like taking this force and substituting it in right there. Now you got 1/2 kxi times, 1/2 xi times kxi. So that's how it gets to be squared. And that's where the 1/2 comes from. If you were to take that spring and stretch it even farther, the equation is still the same. Now you have this final stretch, and you have this final force, and we still are doing 1/2 of the base times the height. And remember that force is really this k value times the displacement. So we'll take this k and x of the final and substitute it in for the f. So now you got 1/2 x kx. So that's the final. The amount of energy at the end is 1/2 kx squared. Thirdly, this is what this question is really asking you to do. Write an equation for the whole thing, so that if we were to take the total amount of energy that was present in this like green one and just subtract the amount that was like from that blue one, that's what we're doing. The change in potential energy is the final amount, so this total thing, minus this little section right here, minus the initial amount. So mathematically, the way to show that would be, here's your final amount minus your initial amount. And all of these are the same, the 1/2 k and the 1/2 k. So you can just pull those out and show that it is 1/2 k, and then it's final minus initial, and that value is squared. And x final minus x initial is the displacement. So regardless of where the spring starts, it doesn't really matter. It is the displacement of the spring that is really important. So then, from there, question 9 asks you to determine the actual potential energy using these values. So remember, it gives it to you in centimeters. You need to report it in meters because the K value is usually done in newtons per meter. Most importantly, it's because the units for energy are measured in joules. Those include meters, not centimeters. So 9A and 9B are demonstrated here. And the final question, question 10, asks you to calculate the change in potential energy when we do it in question 9 compared to question 6. So this is a U. So the change in potential was the final, which we said here, this is your final, and there's your initial. So if you stretch it from 6 to 12, here's the final amount, here's the initial amount. That's a difference of 5.1 joules. If you were to go back to question 6, it shows you that this area totally shaded in is 5.1 joules. So they are the same. So this value here is the same as this value here. Look at that. We love it. Great. Good luck. I hope you do really well on your test. And if you have any questions, come see me.